Environmental Services presents solvated electrons. You see before you a solvated electron solution. It has a characteristic blue coloration, it's electrically conductive, and it is the most powerful dehalogenating agent known to modern chemistry. Application of this process for everything from PCB destruction to chemical warfare agents is now being tested by Commodore laboratories. Here we're pouring some anhydrous liquid ammonia, which is the solvent we typically use for our process, and we will be adding to it some metal. In this case it will be sodium, but we use alkaline and alkaline earth metals including calcium, lithium, potassium, and others. Here we have a small sample of sodium that we're going to be using for this particular demonstration. In the solvated electron process, the metal actually dissolves in the solvent, anhydrous ammonia, forming free electrons and the metal cation. Here you see we add the metal and instantly it dissolves, forming the blue solution. This is a solution of solvated electrons, free electrons. Again, you see the rate of the reaction. We're now adding a little water to the solvated electron solution to demonstrate how the solvated electron solution can be quenched by the addition of water, alcohol, and a number of other materials. The solvated electron solution is very sensitive to moisture and is rapidly quenched, as you can see here, by the disappearance of the blue color. When the electrons are gone, the solvated material is no longer active. Here we're dipping a piece of Teflon in the solvated solution, and you can see the blue coloration on the white Teflon. And you can see that it has had an etching effect. Solvated electrons even attach Teflon. We're now going to take a little methylene chloride and demonstrate the dehalogenating property of the solvated solution. Notice how immediately as the methylene chloride strikes the solution, reaction occurs. This is occurring at minus 30 degrees. And you can see the coloration begins to disappear. However, the presence of the blue swirl, which is a small piece of sodium which has yet to dissolve, is indicative that the methylene chloride has been totally destroyed because solvated electrons are surviving. In this test, we're taking a solvated electron solution. We're demonstrating how it can be applied to decontaminating porous surfaces, in this case a concrete block. The solution is just simply poured on the surface, and as you can see, it will retain its coloration, which means that it is remaining active as it is gradually quenched by moisture in the block, and by moisture in the air you see the formation of white salts, in this case sodium hydroxide. The mixture can be smoothed around and brushed, as can most cleaning agents. And so it is very easily applicable not only to porous surfaces but also to impervious surfaces such as steel, plastics, etc. Here we're adding a little methylene chloride, and as you can see, it immediately quenches the solvated solution, which means that a portion of the methylene chloride has been destroyed. As the material continues to drip, we're building up an excess of methylene chloride where there are no solvated solutions, so we'll have a little bit of excess on here. We add to this now a new solution of solvated electrons, and you see the battle between the solvated electrons as they are in the process of destroying the methylene chloride and gradually overwhelming the system, and the methylene chloride is destroyed. Again, this is happening at about minus 30 degrees, so you don't have problems with the vapors of the methylene chloride being thrown off into the air. The vapors you see are actually anhydrous ammonia coming off. Here you can see we've overwhelmed the methylene chloride. We're now preparing to do a test on a simulated chemical warfare agent. This is malathion, which is a surrogate for some of the nerve agents. We have a beaker of anhydrous ammonia, to which we're going to add a little bit of sodium metal. We have our characteristic blue solution, and we're now adding the malathion. This is malathion in 50% petroleum distillates, so there will be a little different coloration than if we were using pure malathion. You can see the reaction is very rapid, and the destruction of the malathion is complete. It's 100%. You'll see the solvated blue coloration swirling around in the bottom. Again, a small piece of metal which is still not fully dissolved, and the presence of the blue swirls indicating that the malathion has in fact been totally destroyed, otherwise the solvated electrons wouldn't be able to survive. We're now going to do a similar test. In this case, we're going to use hemisulfur mustard, which is a surrogate for the mustard agents. We're now drawing a small sample of the hemisulfur mustard into the pipette. Again, be reminded the solution, the solvated solution, is at minus 30 degrees. As we add the hemisulfur mustard, you see the reaction is very rapid, and almost immediately the solvated electrons are quenched as the reaction goes to completion. We're now going to do a sample with a sample of soil. Here we have a beaker containing a small amount of soil with a stirrer. We're adding anhydrous ammonia to the soil. As you can see, we're filling the beaker with ammonia, and we're now mixing the soil. This is the standard procedure that we use for soil treatments. After the soil's allowed to settle a moment, we hit the stirrer, and you can see it rapidly forms a very fine dispersion that gives us an excellent ability to do both a chemical and physical access by the solvated electron to the contaminants in the soil. You see little pieces of wood and debris floating in the soil, as you would find in real-world situations. And here you see the dispersion. We're now adding sodium to the slurry of anhydrous ammonia and soil and mixing, and as we mix, the PCB contaminants in the soil are being totally destroyed. You see the piece of sodium as it swirls past the camera, and the solvated solution which is being generated by that sodium. Once the kill is complete, we separate the soil and the ammonia either using evaporation or filtration. In this case, we'll illustrate using filtration. You can see we're using a simple Buechner funnel and the head pressure from the ammonia to drive the material through the frit. You see we're collecting clean ammonia in the bottom of the filtration mechanism. Once the liquid has been filtered from the soil, we have a relatively dry cake of soil that has some small amount of residual ammonia in it, and this cake is then removed from the filter, and the residual amounts of ammonia are taken off by evaporation. The ammonia which we filtered off the filtrate is here shown with a small piece of metallic sodium in it to illustrate the fact that the ammonia is suitable for reuse and is recycled in our process. We're now taking the soil off of the filter plate, and we'll allow the small amount of residual ammonia to evaporate from the soil. Again, the soil is at minus 30 degrees. As you can see, as the ammonia comes off, we end up with a very, very dry, friable soil, which is easily mixed into a totally homogeneous resulting mixture. This allows for ease of sampling and minimizes the number of samples that are required. We're now taking some samples of some typical Ohio clays and loams and going to mix them into a pipe reactor to observe the slurrying property of the soil ammonia. The ability of the ammonia to create a slurry of soils is truly remarkable and has been instrumental in the success of the process. You can see we're using a very gummy, sticky clay here, and this is to illustrate how effectively the process can take clay-type materials and break them up into fine dispersions. We're now looking at the soil through the bottom of the reactor, introducing ammonia into the soil, and we will now fill the balance so that the soil is totally submerged with ammonia. Once the ammonia is in the container at the correct volume, we will rotate the pipe on a simple set of rollers that function like a rock tumbler, and you will be able to see how rapidly the soil is broken up into a complete dispersion. Notice how even just by bringing in the ammonia, the soil begins to break up. Within a matter of moments, the two soils which were added, one which is a very high clay, high iron content material from Oak Ridge, and the other which is a mine spoil from central Ohio, are mixed, and a dispersion is formed that totally breaks the soils apart. The large particles you see tumbling are here at the bottom of the reactor, which is tilted at about a 5-degree angle toward the viewer. Here you see at the top half of the glass the suspension of clay platelets as they're beginning to settle. First the large grain sand particles settle, then the silt-like particles separate, which is what we're seeing now, and then the clay particles, which are the finest particles, will hang in suspension for a little bit longer period of time, and then as we allow them to continue to set, the clay particles themselves will settle out of the suspension. The entire process does not take long, as you can see. The top third of the view window now is beginning to show the clear ammonia, and you can see a distinct line of demarcation between where the fines are and the soil. Again, just a simple tumble of the pipe, and the soils are back kicked up into suspension. Scaled on a much larger level, our 200-pound test that we're running now in Marengo is being done in what amounts to a glorified pressurized cement mixer. This cement mixer has the capability of running anything from 100 to 600 pounds of soil per batch. After the ammonia and soil have been mixed and the slurry created, metal was added to the slurry, and the treatment was then complete. After the treatment's complete, the soil in slurry form is transferred into a pipe which rotates in a waterbed, and this allows us to rapidly change the material out of the reactor, which we're doing right now. We're transferring the ammonia soil slurry into the pipe, and we will allow the ammonia to evaporate off from the pipe rather than tying up the reactor. And this allows us to run many batches through the reactor very rapidly. Here you see some of the ancillary processing equipment, which really consists of 2 storage tanks and a simple compressor with a manifold for transferring ammonia. We're now opening the reactor. There is a small amount of residual soil in the reactor after the transfer was complete. We're removing that soil now by means of a vacuum cleaner that collects the residuals into a hopper. Here you can see that the bottom portion of the cement mixer, where the material was drained out through the diamond hatch pattern, still has a bit of ammonia in the material, and as the vacuum cleaner approaches it, the material breaks free and is drawn into the vacuum. As the material is transferred through the vacuum and into the hopper, the residual ammonia is totally removed and the soil is free of ammonia odor entirely. The same reaction can be accomplished in large pipes, which are much more economical than the cement mixer in terms of their construction and fabrication, and they provide an alternative method for scaling the process up and accomplishing treatment of large quantities of materials in the field very economically. The system you're looking at now is a simulation of the system that we would use for treating chemical warfare agents. It consists of two jacketed reactors, and here you can see through the sight glass that we have anhydrous ammonia in the reactor on the left. The anhydrous ammonia is going to be used in this particular illustration to illustrate the reaction of the solvated material with the simulated chemical agent. After the agent has been added, and in this case the agent that we're going to add is carbon dioxide, which is one of the breakdown products of phosgene when phosgene is exposed to solvated electron solutions. After the reaction has been completed, the ammonia can be removed, the reaction salts taken out of this tank. As you can see, the reactions that is occurring at about minus 28 degrees. The ammonia vapor transfers from the reaction vessel to the ammonia collection vessel, which is chilled down to approximately minus 30 degrees, and recondenses in this tank so that the ammonia can be recovered and then recycled directly back over to the reactor, so that we operate in essentially a closed loop system with no discharge of ammonia to the atmosphere. Ammonia is brought in from just an ordinary ammonia storage tank, transferred by a delivery line through a solvator which contains the sodium metal and into the reactor. In this case, we will not be using sodium, we'll simply be using ammonia and carbon dioxide. Again, this is simply to illustrate how the reaction occurs. As we begin to add the carbon dioxide, you'll notice the window starts to darken. As the ammonia and the carbon dioxide react, we form ammonium carbamate. The ammonium carbamate begins to obscure the window, and you see the darkening. With the solvated solution, you would see the same type of reaction you saw earlier in the tape in the small glass, where the solution begins as blue and then turns to a colorless solution as the solvated electrons are consumed. In this case, we're forming ammonium carbamate, and this will begin to show up now as greater concentrations are made as a white precipitate. Again, this reaction is not intended to be represented as destruction of a Chem-D mill surrogate. It really is an illustration of the reactor system that we would propose for handling the solvated solutions and Chem-D mill agents. But you can see the precipitates begin to form. These would then be taken out after the ammonia is removed by transferring them through a filter and into a waste receiver tank. As you can see, the temperature remains well below zero throughout the reaction. Consequently, there is essentially no pressure buildup. You see here the carbon dioxide being introduced and the immediate formation of the salts. We fed carbon dioxide in for over a half an hour at 40 psi into a system that was at essentially 0 psi, and never raise the system pressure because the reaction occurs essentially instantaneously, and as a result, no pressure is built up because the salts immediately the carbon dioxide goes to salts, and consequently no additional pressure is built up. As you can see, we're now at about 15 psi. The entire time the reaction ran, we stayed below 20 psi. Scale up of the ChemD mill process from the small scale reactor can be accomplished actually very simply and very easily. The system that we are currently using in our Marengo facility provides a good illustration of how this scale up can in fact be made. Here you see the precipitate on the window, and you can see the flow rate of the carbon dioxide is quite rapid. Here you see the Marengo reactor. We're currently using this for CFC destruction. The reactor is nothing more than a 500 psi rated pressure vessel equipped with a sight glass in the front so that we can actually see inside to see what's going on. Here you see solution flowing in the reactor, which is recirculating as CFCs are being destroyed. The same basic chemistry that destroys the CFCs is the chemistry that we use for destroying chemical demill agents. Here you see some of the dryers which support the CFC system, because we do recover the CFCs and bring them back to ARI specification. The ancillary and supporting piping would not change significantly for ChemD mill agents, but obviously they would have to be designed to those specifications.